Why do the stars at the edge of a galaxy move almost as fast as those near its center? For centuries, astronomers assumed galaxies spun like whirlpools, faster in the middle, slower at the edge. But in the 1970s, an astronomer named Vera Rubin turned that assumption upside down and possibly changed our entire understanding of the cosmos. Imagine looking up at a spinning ice skater. When she pulls in her arms, she spins faster. Stretch them out, she slows down. Something similar was expected of galaxies. The pull of gravity should make the stars far from the center move more slowly, but that's not what Rubin saw. She mapped the rotation curves of galaxies, tracking the speeds of stars at varying distances from their centers. What she saw defied expectation. The stars on the outskirts were moving just as quickly as those inside, sometimes even faster than anyone could explain by the mass you could see. The visible matter, the stars, the glowing gas, the dust, couldn't provide enough gravitational glue. A passage from the poet Rainer Maria Rilke captures the moment that scientific discovery transforms our understanding. The future enters into us in order to transform itself in us long before it happens. Rilke, Letters to a Young Poet, 1903. When Rubin gazed into the swirling arms of distant galaxies, the future of astronomy entered into us as well. A transformation waiting to happen. Let's pause and reflect. What does it mean when something invisible bends the rules of the universe right before our eyes? To Rubin and her colleagues, it meant there must be something out there, undetectable by light, exerting a gravitational force. This was the invisible scaffolding we now call dark matter. The idea of dark matter, matter that neither emits nor absorbs light, was not invented by Rubin, but her meticulous data dragged it into mainstream science. She collected hundreds of rotation curves from galaxies both near and far. Each time, the same puzzle appeared. If gravity is only due to the stars and gas we see, galaxies should fly apart as they spin. But they don't. The unseen mass, 5 times greater than the visible stars, keeps them intact. Rubin's evidence was overwhelming, and skepticism faded. There is a line from the physicist J.B.S. Haldane. My own suspicion is that the universe is not only queerer than we suppose, but queerer than we can suppose. With Rubin's measurements, the universe suddenly seemed a whole lot stranger. Why didn't astronomers notice this sooner? Part of the answer is technology. Rubin's work depended on powerful telescopes and photographic equipment sensitive enough to capture faint galactic outskirts. But there was also an expectation, a kind of collective bias, that galaxies must obey Newton's apple-falling rules. When observations didn't match predictions, many dismissed them as experimental errors. Rubin pressed on, double-checking her methods, consulting with skeptical colleagues, refusing to accept wishful thinking over data. A line from Shakespeare's Hamlet comes to mind. There are more things in heaven and earth, Horatio, than are dreamt of in your philosophy. Rubin's discovery widened the scope of astronomical philosophy. There was more to the universe, quite literally, than met the eye. Dark matter isn't just a puzzling leftover from Rubin's work. It forms the backbone of modern cosmology. Galaxies and galaxy clusters are wrapped in massive spherical halos of unseen matter. Without it, computer models show galaxies would never have formed as they did. The visible universe is just the foam on an invisible cosmic ocean. Vera Rubin's persistence reminds us that cracks in our understanding often reveal doors to new worlds. She advocated relentlessly for more women in science too, opening another kind of invisible door. So what exactly is dark matter? Despite decades of effort, we still aren't sure. It doesn't interact with light, and it rarely bumps into ordinary matter. Some imagine mysterious particles, weakly interacting massive particles or WIMPs, while others propose stranger stuff, axions, sterile neutrinos, or something not yet conceived. Experiments in deep mines, orbiting satellites, and gigantic underground detectors keep searching for proof. But so far, dark matter remains the most successful unconfirmed theory in science. These words from Carl Sagan capture the spirit of curiosity that Rubin exemplified. Somewhere, something incredible is waiting to be known. The story of Vera Rubin's rotation curves is a story about paying attention, insisting on evidence, and accepting that the cosmos has more secrets than we thought. Now, let's trace the steps that turned Rubin's finding into one of the most important scientific mysteries of the modern era. First, the puzzle. Stars on the edges of galaxies move too fast, as though something invisible is adding gravity. Second, the skepticism. Could there be a mistake in how we measure the stars' speeds? Rubin's careful methods with spectrographs and comparison stars silenced many doubters. Third, the implication. If dark matter is real, then all our physics, all our models of the universe, need updating. Fourth, the search. If we can't see dark matter, can we detect its effects elsewhere? The answer seems yes. Galaxies cluster together in ways ordinary matter alone can't explain. Gravitational lensing, bending of light from distant objects, shows patterns consistent with vast quantities of invisible mass. A poet might say that the universe wears a veil, and astronomy is the art of learning what lies beneath. Rubin's own words, spoken in a 1996 speech to young scientists about the joys of scientific discovery. Don't let anyone keep you down for silly reasons. What you discover is yours. What you find, no one can take away from you. Her work, and her insistence on clarity, illustrates that true discoveries require both patience and courage. So, how did all this change the way we see the universe? Before Rubin, galaxies were understood as isolated islands of stars. With dark matter, galaxies became nodes in a vast, invisible web, shaping the growth of everything we see. Cosmologists now estimate that only about 5% of the universe is made of atoms like us. The rest is dark matter and dark energy, unseen and largely unknown. If you're wondering whether dark matter could be made of black holes or cold clouds of gas, astronomers have mostly ruled those out. Black holes and gas would give off radiation or show up in gravitational microlensing surveys. The invisible backbone must be something even stranger. Particles that barely touch the world of light and atoms. From the ancient Greeks who named the Milky Way, to Newton's spinning orbits, to Vera Rubin's cold, clear evidence, humanity's idea of the universe keeps expanding. Rubin shows us that the biggest secrets can be hidden in the data, waiting for someone to really look. Let's step back for a moment. What does it mean, philosophically, that most of the universe is invisible to us? Are we, like the fish in Plato's cave, mistaking a dim shadow for the full reality? Rubin's findings urge us to imagine a cosmos far grander than our senses would suggest. Consider Emily Dickinson's line, "The brain is wider than the sky." Rubin's persistence widened not only what we know, but what we can imagine knowing. Her story is a reminder that every time we question the obvious and test our ideas with fresh evidence, the universe gets a little bigger. As for dark matter, the search continues. New telescopes, particle detectors, and ever more sensitive instruments scan the cosmos for a trace, hoping to make what was once invisible finally visible. But Vera Rubin's work reminds us that some mysteries are so profound they can shape science even when no one can see them. Next time you look up at the stars, consider this. Most of what's out there is hidden. and discovering it takes both careful eyes and the courage to trust them. Vera Rubin did both, and the universe was never the same.